Happy Thursday, guys. We're almost at the end of the week. Today's lesson is on London dispersion forces, and London dispersion forces are a type of intermolecular force that occurs between nonpolar substances. So between nonpolar molecules. Now, that might seem kind of strange that you could even have intermolecular forces between nonpolar things. For instance, if you have an argon atom. So an argon atom, you remember, is a really stable atom. It's element 18. It has 18 electrons. 1s2, 2s2, 2p6, 3s2, 3p6. And it's got a stable octet. It doesn't have a tendency to take electrons from other atoms or to give away any of its electrons to anybody else. It's perfectly content on its own. And if you think about it, since it's just an atom with some electrons in the nucleus in the middle, all right, it's really balanced out, okay? The valence shell is filled up and it's neutral, okay? So there's not a positive or negative charge on this thing at all. So it's neutrally charged. Okay, if anything, if you think about it, it seems like argon atoms would have a tendency to repel each other because all you have are these electrons surrounding the positively charged nucleus. And so if two argon atoms were to approach each other, why would they start sticking to one another? It doesn't make much sense. It seems like, if anything, the electron clouds would kind of repel each other. Okay, since neither one of these are reactive, there's no space in the valence orbitals for extra electrons. So they're neutrally charged at any rate, and it also seems like, if anything, maybe they would just repel each other. But that's not what happens. If you get argon really cold, it will start to liquefy. And so the fact that it does liquefy tells you there must be. So there must be some type of attraction. It's a weak attraction because you got to get these molecules moving really slowly. In other words, get the sample really cold. And I've forgotten actually how cold you have to get it. Let's see if we can look it up on periodictable.com. I think it's around negative 190 or something like that. The boiling point of argon, let's see. Oh, that's the melting point. The boiling point, negative 186. Okay, so if we can get it down to negative 186 Celsius, then it will liquefy. Okay, and so when that occurs, when you have all these gas particles that suddenly start sticking to one another, that tells you there must be a type of attraction. So London dispersion forces is a theory that helps us understand how this could happen. Okay, and it's a pretty good theory. It's based off of everything that we've already learned about the atom, about electron configurations and the movements of the electrons. So let's consider how this would happen. How can we go from the gaseous state into the liquid state where the particles are much closer together and they can slide past one another now, but they're sort of sticking to one another. How could that happen? Gaseous. And then liquid. Okay? How could that happen? So back to the argon atom. what we want to do is imagine, here's the nucleus, positively charged in there, right? Positive 18, because there's 18 protons, element 18. And then out here, you've got the electron cloud. Now, what do you remember about the electron cloud? Is it really, really predictable? No, the electrons are all over the place at once, it seems, and they also seem to be a little bit like fireflies. In other words, you can't really predict where they're going to be at a given moment, what they're going to do next, and it's possible they could be anywhere in theory. And so we might imagine this electron cloud as really, really spherical at first, but then maybe the next instant, some of these electrons happen to be over on the right-hand side of the atom, and then there's less electrons on the left-hand side of the atom. So here's the nucleus still, 18 positive charges. And the electron cloud happens randomly to kind of shift over here like that. Okay, just for an instant. Okay, and what this creates is something called an instantaneous dipole moment. Because right now, the electron cloud is no longer perfectly symmetrical. There's a little bit more negative charge on the right-hand side than on the left-hand side. So for that instant, it happens very quickly, and it's random, because electrons kind of are random. You don't know where they're going to be. For that instant, you end up with a partially negative side of this atom and a partially positive side of the atom. Now, technically, the whole thing is still neutral, but it's just that electron density, you have more of that over here than over here. And so it leaves behind a little bit more positive charge from the nucleus because the electrons are a little bit more on this side. So this is called an instantaneous dipole moment because it only happens for an instant. All right, so just for a moment, you end up with a dipole moment. Okay. And so that's the idea of an instantaneous dipole moment. And it's going to help us understand how London dispersion forces work. It's all based on this instantaneous dipole moment thing. Okay, so in a sample of argon, you got to remember there's many, many argon atoms moving around. So let's consider what would happen if you had an instantaneous dipole moment in this atom, and then there was another atom nearby. Okay, so I'm going to draw two different atoms here. So again, argon, 18 protons in the nucleus, and now we've got this the second atom nearby. And let's pretend they both start off kind of symmetrical. But now let's say this atom ends up with an instantaneous dipole moment. Just for a brief moment. Right? And this atom nearby, its electron cloud is going to be affected by what just happened right here. Suddenly these electrons have moved this direction randomly, and what happens is they sort of repel these electrons and they end up shifting. So now they shift in a similar way. And we get that same type of instantaneous dipole moment in this atom. And that was a result of the first instantaneous dipole moment. This negative charge here repelled these electrons. And now check this out. Now we have a negative charge here and a positive charge here. That's an intermolecular force. And that's what we call a London dispersion force. Just for a moment, this instantaneous dipole moment has induced or created an instantaneous dipole moment in a nearby neighboring atom. And now we have a positive charge and a negative charge which attract. Okay, so compare that with what we learned about dipole-dipole attractions yesterday, right? In dipole-dipole attractions, you have these permanent positive and negative charges because you have polar molecules, right? So in the water molecule, permanent partial negative on the oxygen, permanent partial positive on the hydrogen, because you have these polar bonds in a polar molecule. So these polar molecules can attract one another. So now we can see we get a similar type of thing for an instant with nonpolar particles like argon atoms. Okay, so I'm going to show you a quick little PowerPoint slide, actually a couple slides, kind of recapping everything I just said. So London dispersion forces. So nonpolar molecules can also exert forces on each other. Intermolecular forces can happen. And we know that because otherwise liquid argon wouldn't be possible. Okay, it would be in the gaseous state all the time. Without intermolecular forces, solids and liquids aren't possible. And the whole idea is that electrons are not evenly distributed at every instant in time. You can have an instantaneous dipole moment in a particular particle. Even if it's nonpolar, on the average, at a given instant, you can get an instantaneous dipole moment. And that induces a dipole in the next atom that's nearby. And that creates something called an induced dipole interaction. You don't need to know that last phrase there. These are just called London dispersion forces. So I gave an example with argon. Let's look at a different example. Hydrogen, diatomic hydrogen molecules. So let's imagine we have two diatomic hydrogen molecules. Each one is nonpolar. It's a nonpolar bond. But between those hydrogen atoms in each molecule, like right in here, two electrons are buzzing around in here, being shared by these atoms. But since they're kind of like fireflies, it's possible that one of these electrons, or maybe even both of them, for an instant shifts over to one side of the molecule. All right, so randomly, boom, you get an instantaneous dipole moment. Partial negative over here, partial positive. It could have been the other way around because it's random, but let's pretend it's this way. So now we've got this partial negative charge and it's nearby this molecule. So this molecule was doing its own thing, and now its neighbor suddenly has this instantaneous dipole moment, and this one can't remain perfectly neutral and symmetrical anymore because here come these negative charges showing up nearby, right? So that's like a pressure. And so it induces these electrons to shift over here, and it leaves behind a positive charge. So now we have positive attracting negative. Okay. I don't know if you guys have ever heard of starlings. They're a type of bird. A few years back, I saw some really cool footage online of big formations of starlings, and they group up together and they make these beautiful patterns. And when I saw it, it made me think of London dispersion forces. You probably think I'm crazy, but here's a big flock of starlings, and we can think of this as being like something in the liquid state. Okay, so each individual bird in here is like a particle, and there's got to be thousands of these birds, literally. Okay, but when they make this flock, and I'll click the video on here, you get these amazing patterns, And they're all kind of moving in unison. They're all kind of stuck together in a sense. And if you start wondering, like, well, who's controlling what's happening here? Like, who's making the decisions? It's all kind of happening at once, right? And it's not like one of them is deciding, hey, let's go to the left or let's go to the right. But as soon as one of them starts moving, it sort of induces the same type of movement in its neighbors. And I personally think this is a lot like the liquid state for nonpolar substances. Okay, so anyway, when I saw this, it made me think of London dispersion forces, right? You imagine one bird and it flaps its right wing a little bit extra, and its friend, its neighbor, feels that pressure from the air, and it responds almost immediately. So the behavior of one bird affects everything around it. Okay, and so if you go back and you imagine these London dispersion forces, right? If you had trillions of hydrogen molecules, you'd have all sorts of induced dipole moments happening in all sorts of directions, and yet they would all kind of adhere to one another like that flock of starlings is doing. Okay, so that's London dispersion forces. It is a theory. It's kind of like, how do we know that this is actually happening? Well, you can kind of extend out the theory and make some predictions. Okay, so because a good theory, you can use a good theory to make predictions and see if those predictions are true, and that would kind of help authenticate or validate, rather, your theory. So we know that these are weak and short-lived. These are instantaneous dipole moments. Non-polar substances, you got to get them really cold in order to get the liquid state from the gaseous state. Okay, so this theory is showing something that's kind of instantaneous and it's kind of random. It's not a permanent dipole moment. So it makes sense that these would be short-lived and therefore weak. Okay, and the fact that we got to get these substances really cold sort of reinforces that idea. It validates that idea. If we can get a really low temperature, everything starts slowing down, the particles spend more time near each other, the electrons are moving slower, and these London dispersion forces start getting stronger in a sense because things are moving slower and they have more of an opportunity to affect things nearby. Okay, and so eventually these particles are so close to one another, they're moving slowly, those weak London dispersion forces become relatively more important and the particles stick to one another. Okay, and here's another prediction that this theory would allow us to make. If you have more electrons, that should mean that the electron cloud is more polarizable. In other words, I was talking about argon a moment ago. Argon has 18 electrons in its electron cloud, but xenon has 54 electrons in its electron cloud. And so it seems to make sense. If you have more electrons, you have more of a chance to get an instantaneous dipole moment, right? If you only have 18 electrons to work with, there's only 18 little particles that might happen to be on one side of the atom at a given instant. But if you have 54 electrons, it's a lot more likely you could get an instantaneous dipole moment because 54 electrons gives you more of an opportunity for that instantaneous dipole moment. So the prediction would be, if I have more electrons, the atom or the nonpolar molecule would be more polarizable. It could get an instantaneous dipole moment more easily, and so then maybe these London dispersion forces would be stronger if I have more electrons. And that's exactly what we see in the data. So xenon could randomly have an instantaneous dipole moment more easily than neon, say. By the way, neon has 10 electrons. There are more ways for the electrons to be unevenly distributed around it. Okay, so The idea is for neon, if you only have 10 electrons here, you only have 10 particles which might happen to be on one side or the other to get the instantaneous dipole moment. But if I've got 54 electrons, like in xenon, there's a lot more ways, it's a lot more probable I could get an instantaneous dipole moment. And so now check this out. The prediction would be stronger London dispersion forces the more electrons I have. So let's look at the data to finish up for today. Back to the periodic table. Let's have a look at the boiling points of the noble gases. So here's the boiling point of neon, -246, so really cold, and then xenon, -108. So -246, that's tremendously cold. -108 is still tremendously cold, but it's a lot less tremendously cold. It has a higher boiling point. In other words, more temperature is needed to break apart their intermolecular forces. And actually, if we go down the entire column, you see a very clear pattern. Increasing boiling point. Helium, -269. Neon, -246. Argon, we just saw it, -186. -153 for krypton, -108, and then radon, -62. Okay? And so, again, looking at that pattern, getting larger and larger boiling points. Okay, so that means stronger and stronger intermolecular forces. We also see the same pattern in the halogens. All right, let me go back a couple slides ago. We were talking about the halogens the other day, right? Now the halogens are actually all nonpolar molecules. Fluorine is a gas, chlorine is a gas, bromine is a liquid, iodine is a solid. And so what we see is the strength of the intermolecular forces is increasing for these nonpolar substances. Why would that be the case? Fluorine, diatomic fluorine, has less electrons than diatomic chlorine, which has less electrons than bromine, which has less electrons than iodine. So we're getting larger and larger electron clouds as we go down, right? So size of electron cloud is getting bigger and bigger and bigger. So basically more electrons, right? Fluorine, diatomic fluorine would have 2 times 19 electrons. Sorry, not element 19, element 9. 2 times 9 electrons. Chlorine, 2 times 17. Bromine, 2 times 35. And iodine, 2 times, I think it's element 53. Let me double check those numbers. Element 9, 17, 35, 53. I don't have my atomic numbers memorized as well as my atomic weights. All right, so 9, 17, 35, 53. Okay? So we're getting more and more electrons. This is 18 electrons. This is 34 electrons. This is 70 electrons. And this is 106 electrons. More and more electrons, stronger and stronger intermolecular forces. Why would that be the case? Because the electron cloud is getting more polarizable as we go down this direction. More polarizable. In other words, more of a chance of a given instantaneous dipole moment. And if you can get more instantaneous dipole moments, you've got more of an opportunity for these particles to attract each other with the London dispersion forces. Okay, so stronger intermolecular forces. Stronger London dispersion forces for these nonpolar halogens. All right, so that's the lesson on London dispersion forces. Let me know if you have any questions. Set up a Zoom appointment if you would like to, and I'll see you tomorrow in the Zoom class. Bye.